The flexibility of software systems means they can be designed in a variety of different ways. But we want our systems to be easy to understand, quick to diagnose and fix, and amenable to future change when we want to add new features. All systems start out this way. When you only have one line of code, it is easy to understand, easy to fix, and is amenable to future changes. But over time, as we add new features, we end up extending the design, violating the design, obfuscating the features that are in there already, and this makes the code harder and harder to maintain. So we really want to think about our design in an upfront and intentional manner. Ultimately, what we want to do is find a set of design principles to help guide us towards making good decisions. But before we look at design principles, let's take a step back and look at some design symptoms. Now, this isn't a comprehensive list. There are lots of different symptoms of poor design. But here are some high-level tips that can help us think about the designs that we've come up with when we're evaluating design A against design B. A rigid design is a design that's resistant to change. We can see these in our own systems when we go and make a change in one small module that ends up propagating across the breadth of the system. Rigid designs are challenging in practice because they make effort estimation really hard. If you don't know what that propagation is going to look like, figuring out how long a task will take is challenging up front. It also makes assessing risk challenging because, again, we also don't understand that propagation path for the changes we're making to our systems. Design fragility arises when we have a design that's easy to break. Designs that make a lot of assumptions about the context in which they're going to run or are lax in their pre- and post-condition checking often exhibit design fragility. One common example of software fragility is when we're fixing bugs and we end up changing code that has no logical connection to the bug itself. This exacerbates both fault localization tasks and future program understanding tasks. Next, let's talk about design immobility. At the individual line level, most lines of code are not truly unique. So if you have some code that you've written before, or there's some code that you know exists within your company or on the internet, you might be tempted to just go and reuse it. This kind of task is known as clone and own, or pragmatic software reuse. So what you do is you're going to search, and you'll find the code that you want, and you'll copy it into your system. And you realize, oh, that code has some dependencies on some other modules or classes, and you'll copy those into your system. And after a few hours, you'll realize that you keep copying more and more and more of the code into your system, and you realize you just can't do it. The code that you want is too tangled with its original context for you to actually reuse it effectively. Now, this is the kind of task where you might think that refactoring is exactly the right thing to do. Right? What we want to do is take that code that's tangled with its original context and extract it and turn it into a reusable module. And that's great for you as the person who wants to reuse the code. But as the original owner for the code, they only derive risk from this operation because the code was working for them before, and these kinds of large structural changes are often risky. Software with viscous designs make it easier to violate the design than adhere to it. This is problematic because it leads developers to introduce hacks to their system in order to make the code work. And those hacks lead to the accrued technical debt that a system has. Viscosity also applies to the processes used within the software system. So if, for instance, the build system is slow or the test system is slow, developers will go and batch their changes together and submit them in big bunches so that they can accrue those slow steps all at once, even if it's not the safest way to proceed with the development on their systems. Software is often created to solve complex problems, and we live in a complex world. Because of this, it's unsurprising that the systems we end up building end up being complex themselves. As developers, we like to build systems that we can use for future uses as well. This fitness for future often drives us towards building abstractions into our systems so we can easily augment and extend them in the future. However, overbuilt abstractions are one source of needless complexity. Abstractions do make our systems harder to understand, so we need to be very careful about the abstractions we introduce into them. While in some cases these broad abstractions might be really useful, for instance if you're designing a general purpose library, in other cases abstractions that don't end up being used in practice just end up adding cognitive overhead to the developers who are trying to modify and understand your systems in the future. Next, let's talk about repetition. Software systems are so large, they exceed the ability of a single developer to understand the entire breadth of the entire system. So if a developer adds a new feature by copying some code from one part of the program into another, they might solve their problem. They'll add that new feature, but they also introduce a clone. These clones are problematic because if we find that there's a defect in one of these blocks that has been cloned, we have to find all of the places scattered across the system where these clones exist and update them consistently. Often, clones indicate some type of simple abstraction is missing from the system. Systems tend to become harder to understand or more opaque over time. This happens when developers add new functionality into convenient, if improbable, locations in their code. This can often be seen when developers are reluctant to add new classes to their systems, and instead glom functionality onto existing abstractions, whether they make sense there or not. This can really make it hard for the code to communicate its intent, which inhibits future program understanding, bug fixing, and feature additions.